In the previous video, we have completely analyzed the acid-base behavior of pure water. However, this is certainly not interesting from a physiological point of view, and we're going to apply the same technique as Peter Stewart by adding constituents to our pure water so that it becomes a better and better approximation to blood plasma. In this video, we will add what are known as strong ions. At this point, a definition, which was mentioned in a previous video, is required. Strong ions are species, or ionic species, that when present in solution are essentially always in fully dissociated form. An example may be useful here. Imagine throwing some table salt into a glass of pure water. As you know, table salt is sodium chloride, or NaCl, and the reaction that takes place is sodium chloride dissociating into sodium plus and chloride minus ions. What is important about this particular dissociation reaction is that there's almost no NaCl in solution. For practical purposes, 100% of it becomes Na plus and Cl minus. Thus, we don't need a dissociation constant because it is almost infinity, and we may as well simply accept that for all practical purposes, it is always in fully dissociated form. We thus define strong ions as ionic species which are always found in fully dissociated form for all practical purposes. And clearly sodium and chloride fit this definition. It should be clear from our previous video on pure water that hydrogen and hydroxyl ions are clearly not in this category. That is, they are weak ions as their dissociation is far from complete. In fact, it is quite minimal. Other examples of strong ions include potassium and certain organic acids such as lactic acids and ketones. In reality, these organic acids do have measurable dissociation constants. However, they are sufficiently large that under physiological conditions, they are found in almost completely dissociated form and may thus be considered strong ions for the purposes of this analysis. Now imagine adding some drain cleaner, sodium hydroxide, to our pure water. Clearly, there are two ionic species, namely Na+, which is a strong ion, and OH-, which is a weak ion. Thus, we can safely assume that the sodium will always be fully dissociated, while the hydroxyl is free to combine with H+. Thus, hydrogen ions and hydroxyl ions are weak electrolytes, as they are substantially combined in solution. However, the electrical neutrality condition imposes a constraint on this. Note that it is not possible to add pure sodium because it is not electrically neutral, but adding sodium hydroxide, or NaOH, complies with the electrical neutrality requirement. We can also add hydrochloric acid, or HCl, to the solution, where the Cl is another strong ion, this time negative, and hydrogen is the weak ion. So, in this case, we've added a strong cation, Na+, and a strong anion, Cl-. And as you will see shortly, the cation makes the solution more basic and the anion makes it more acidic. Once the strong ion has been added in this way, we have a new set of conditions which translate into two simultaneous equations. These are H+ concentration times OH- concentration is equal to K'W, as before, and electrical neutrality, which requires that there is no net ionic charge, so that sodium concentration minus chloride concentration plus hydrogen concentration minus hydroxyl concentration equals 0. This is just a simple statement that the cations must equal the anions in order to preserve electrical neutrality. But note that we have grouped the strong ions in brackets. We now introduce a new term which is critical to Stewart's analysis of acid-base. That term is the strong ion difference, or SID. SID is nothing more than the difference between the concentrations of strong cations and strong anions. We generally write it with square brackets to indicate that it is a concentration-like term, and its units are concentration units in keeping with the units of our other analytes, such as millimoles or moles per liter. But note that SID is not a true concentration, but rather a difference in concentration. And unlike true concentrations, it can be negative as well as positive. In blood plasma, under normal physiological conditions, the main strong ions are sodium, potassium, and chloride. And if you add those cations and anion and single anion in their appropriate physiological concentrations, we end up with an SID in normal human plasma of approximately 42 millimoles per litre. The other strong ions have very small concentrations under physiological conditions, and we can ignore them for the time being. We can rewrite the electrical neutrality equation by replacing the difference in strong ions that you saw in brackets earlier with the term SID in square brackets as follows. SID plus hydrogen ion concentration minus hydroxyl ion concentration equals 0. Our second equation remains our well-known water dissociation reaction, which, as we mentioned previously, is H plus concentration times OH minus concentration is equal to K prime W. Now we can solve the two simultaneous equations for H plus and OH minus to get the following. Hydrogen ion concentration is equal to the square root of K prime W plus SID squared over 4 minus SID over 2. And the OH minus concentration is similar, but the minus sign is replaced with a plus sign. This is completely unimportant from your perspective. All you need to worry about is how we get the two simultaneous equations. The solution is actually irrelevant except to the computer. This produces the following graphs for H plus and OH minus as a function of SID. Note how the graphs of hydrogen and hydroxyl ions look almost like perfectly straight lines, suggesting that as we make the SID more negative by adding hydrochloric acid, for example, it appears as if each mole per litre of hydrogen added in the form of hydrochloric acid makes the hydrogen ion concentration increase by 1 mole per litre. However, this is not actually perfectly true. It is not the hydrogen ions that we are adding to the solution, but rather the strong chloride ions that make the difference. Likewise, as we add sodium hydroxide, it is not the hydroxyl ions that is affecting the solution, but rather the sodium ions. In other words, the graphs are not even true straight lines. If we zoom in to where the graphs cross and magnify the image, we see the following. As you can see, these are curves and not straight lines, making it evident that the change in H plus and OH minus concentrations are not actually linearly dependent on the amount of H plus and OH minus added. While our objective is to move towards blood plasma, the solution we have just created is similar to stomach acid with hydrochloric acid and shows what determines the pH of the solution.